Okay, so just a small recap of what we were doing last time. We studied different modes of heat transfer. Okay, and what were the three modes of heat transfer that we studied? The first one was conduction. Conduction, okay. Well, conduction was governed by which law? Name of the law. Fourier's law. Fourier's law. Okay, you should remember the name. Okay. Fourier's law. Okay, and what was that law? Q is equals to minus K A dt by dx. Right? That was the law. Then the second law was the convection. Okay. Yes, convection was by Newton law of cooling, and what was that? Q is equals to HA Ts minus T infinity, right? Then the third was the radiation, and it was, what was the law? Stephen-Boltzmann law. And what was the law? Q is equals to HR A surrounding. Okay. Now what about HR? What was the formula for HR? Emissivity, epsilon, sigma. Okay. Ts plus T surrounding multiply by Ts square plus T surrounding square. Okay, these were the formulas that we studied. These were the laws that we studied last time, and we applied them in the numerical as well. Okay, so now we are going to continue with it, what we did. Okay. So we okay. Now let's move on with it. Thermal resistance.
The last one, to
Yeah.
find the radiation Q.
Yes.
How to find it? By this law, by the emissivity.
It was found in two ways. Well, this was found before as well. These are two different ways. One way we solved that way. This way is also okay, but even if you solve it by that way, it's good enough as well. Okay. Okay, thermal resistance. Now, let's first understand the concept of resistance. Look, there is a general law of the universe. The universe created by God, and God made one specific law which is followed everywhere in every field. Okay. Now, let me give you from an example that you studied and you're well aware of in the electrical systems. Okay, you know Ohm's law. What's Ohm's law? V is equals to IR, or I can write here RI, right? That's the Ohm's law. But this law is basically the universal law which is applied in electrical engineering. This law is basically a universal law which is applied in electrical engineering, becomes the Ohm's law. Now, what does this law say? This law say when you have a potential difference, V is what? Voltage. Voltage is a potential difference. When you have the potential difference, then you can make the electrons to flow, and that flow of electrons is known as current. Okay. However, the flow of electrons will be resisted by the resistance in the wire. Right? Am I right or not? This was the law. Okay. So if I make it in the general form, so V is the potential difference, right? In electrical systems, it's voltage, but in reality, it is the potential difference. So potential difference is equals to R is the resistance, okay, is equals to resistance to flow, and I is basically the flow. It is the flow of electrons in electrical systems, but in generally it is the flow. Okay. So potential difference is equals to resistance to flow multiplied by the flow. This is the universal law. It is applied everywhere in the world. In every field it is the same. For example, in the electrical systems, it is V equals to IR. You also studied that in the mechanical systems. In the mechanical systems, the flow was the object moving itself. So that was the acceleration, right? So flow was A. Okay, the potential difference was the force applied. Force was the thing which caused the body to move, right? Here potential difference is the thing which caused the electricity to flow. So force was the thing which was the potential difference, F. And the resistance was mass, because larger the mass, harder for it to flow. Smaller the mass, easy to flow, right? So that was F is equals to ma. This was in the mechanical systems you studied. That's the general law of universe. Similarly, in the fluid systems, you studied that as well. Okay. Now, in the fluid system, what is the thing that flow? It's the fluid which flows, and we call it determine it with m dot, mass flow rate. Okay. So thing that flows is m dot. Okay. What is the thing? What is the reason for the mass to flow? What is the reason for the mass to flow? What is the thing that causes the mass to flow? Pressure difference. You need to generate a pressure difference for the mass to flow. So the potential difference here was delta P. Okay? And then you have the resistance. You studied this formula?
No, that is the M multiplied by density.
M multiplied by?
M multiplied by the density.
That is different. That's you did not study any relation where delta P and m dot are related. Anyways, there is a relation. It's the same law in the fluid systems. Okay. You studied the parallel and series flow in the fluid. Parallel flows. If for example, if a water is going. No, laminar turbulent is something else. But a flow is going, okay, from a pipe, and then it is distributed into 3 different pipes. That's a parallel flow.
Yeah, and to measure the mass flow rate from
And head
inside
losses.
outside pipe.
Yes.
And the head losses.
And the head losses, yes. Okay. anyways. So, like in electrical systems, you have the parallel circuit, you have the series circuit. So, in all these systems, you have the parallel and the series systems. Okay. So, anyway, that was the electrical, the mechanical, this is a fluid system. In the similar case, in now you are studying heat and mass transfer, that's the thermal system. The thermal system also follows the universal law. As I told you, universal law is same in all the fields, whether you go into electromagnetic field, physics, chemistry, mechanical, electrical, fluid system, heat transfer. It's a universal law made by the God, it's same. Okay, so in the thermal systems, okay, what is the thing that flow? It will be the heat. Heat is the thing that flow. Okay, so I write here Q. Okay, now what is the thing which causes the heat to flow? Different temperatures. You need to have temperature difference for the heat to flow. So you will have delta T here, right? And then you will have here resistance. Okay, so that will be the resistance in the thermal systems. Now we can find the resistance in the thermal systems for all the 3 processes. We can find the resistance in the thermal systems for all the 3 processes. Okay, if I want to write it, I can write it like Q is equals to delta T upon R, right? I just rewrote the equation. Q is equals to delta T upon R. Okay. Now, we use this equation and apply it here. Your Q is here, right? Delta T will be, okay, let me write it in form of delta T. I told you if I write it in the form of delta T, then negative sign goes, okay? So it's Ka delta T by delta X, right? So Q is there, delta T is delta T. What will be 1 upon R? Here we have 1 upon R, right? So 1 upon R will be Ka over delta X, right? Yeah. So this will be Ka over delta X. Is it right?
Okay.
So because this is Q, this is delta T, Q equals to delta T upon R. So what will be 1 upon R? 1 upon R will be Ka upon delta X, right? So what will be R? R will be delta X upon Ka. So that will be the conductive resistance. Got it? So conductive resistance will be delta X upon Ka. Okay. Now, in the similar fashion, we can find the convective resistance. R convection. So what will be R convection? Now you tell me.
Delta T can be expressed as
Yeah, sure. Here in this case it is delta T. Okay. So delta T is here. Q is here. So 1 upon R is HA. So R will be 1 over HA, right? So it will be 1 upon HA, right? What about R radiation? Just HR, 1 upon R HRA. Is it right? So these are the thermal resistances. We have found out the thermal resistances for the conduction, convection, radiation processes, right? Now tell me one thing. Look at this equation. Can you find the unit of R? What will be the unit of Q? What? What will be the unit of delta T? Kelvin. So what will be the unit of R? Kelvin over watt. Okay. So R unit will be Kelvin over watt. Right? So whether, because this is the same formula, so the unit of R would be same. Whether it's R conduction, it's Kelvin over watt. Where R convection, Kelvin over watt. R radiation, Kelvin over watt. Got it? So that's the thermal resistance.
should be proven.
No. If I ask you to prove, then you prove. Otherwise, use directly. Okay. The better thing is that, do you have the formula book in the soft form? You don't have the formula book in the soft form? I think I gave you. Okay. So distribute it and go through it while you are going through the lectures. Go through the formula book so that you know what formulas are available. Because what formulas are there in it, obviously they will be there with you. But what formulas are not there in it, you have to remember them. But anyways, this is a big book, 44 pages. So many formulas are there. Okay. Anyways, is there anything that you don't understand in it? So please ask.
For the resistance, delta T is equal resistance divided by Q. Resistance here came from where? From the tape or from what?
Resistance come from where? If it is conduction, then the resistance is in the material of the conduction. material of the pipe material. If it is convection, then the resistance is because of the air. So air or water, whatever is causing the convection, the material itself provides the resistance. Like for example, in electrical systems, the wire from where the electric current is passing, that wire is providing resistance. So resistance is always provided by the medium through which the flow occurs. Okay.
It was radiative. It was radiative.
If it was radiative, again, radiations pass through a medium. Okay. For the radiation, if there is no medium, it's best no resistance. Like for example, an energy coming from the sun, which passes through the space vacuum, no resistance. But in the earth, okay, the radiation, for example, the radiation cannot pass through this wall, okay, because it's providing resistance. It can pass through air, very hardly pass through water. Most of the time, 90-95%, it cannot even pass through water, okay. And if it is solid body, opaque object, cannot pass at all. So that's the resistance. It's providing resistance. Okay. Any other question? So anyways, that was about thermal resistance. Okay. Now let's move ahead. First law of thermodynamics. You studied that first law of thermodynamics. It's as simple as that. Energy in is equals to energy out plus energy stored. Yeah, energy in minus energy out is equals to energy stored. It's like that. Okay. So there is some description written over here. I don't need to go through it because I'm sure you know it. You studied the course of thermodynamics. If you don't remember it, you can just go through the description as a revision for you. Okay. We have closed systems, we have open systems. It's delta E is equals to Q minus W. Okay. We went through it in big details before. Okay. Now the energy forms, total energy is composed of mechanical and internal energy. Okay. Mechanical energy is kinetic plus potential. Internal energy is thermal energy plus chemical energy, whatever the binding force is. Thermal energy could be sensible and latent. Do you know the concept of sensible and latent energy? Any energy which can be sensed by thermometer is sensible energy. So you have water and you start heating water. The heat is being supplied to the water and you can sense it by the thermometer as the temperature rises. So that's the sensible energy. But once water reaches 100 degrees centigrade, it's now about to boil. Now more heat you provide, temperature will not change. So now the energy that you are providing cannot be sensed by thermometer. Although you're providing energy, but it is used for boiling and the temperature remains same, cannot be sensed by thermometer, so it's not sensible. Then it is called latent energy. So any energy that can be sensed by thermometer is the sensible energy. Okay, anyways. Just read this yourself. There's nothing in it new. You studied this as well. H is equals to Cp delta T. Instead of H, they have written enthalpy as I here because H is something else here. What is H here? Convective heat transfer. Don't want to confuse. Okay, anyways. So just leave it. Okay, let's come over to a numerical. As I told you in this course, the biggest problem is first to understand the scenario, because the heat and mass transfer is applied in every field of life. Okay, from human body to large mechanical systems to simple running objects, and everywhere heat and mass transfer is applied. So you have to first understand the scenario where it is applied, and then you can actually apply it. So understanding the scenario is another huge task. Okay, so this is the biggest problem with this course. So you will have 10 problems, and for the same equation, but one problem will be related to some electrical mechanism, one problem will be related to the human body, one problem will be related to large power plants, one problem will be related to simple running objects and things like that. So variations in field where this can be applied, and that becomes a bit difficult for you to. But anyways, you have a lot of homework problems here, and a lot of classwork problems will be there as well. So with practice, you get used to it. But anyways, this is the thing which is problematic in here. Let me just rub it. Okay, now this problem is related to a wind turbine. What is a wind turbine? Wind turbine is a device which uses wind energy to produce electricity. And how does it work? It has some fan. So when the wind blows through the fan moves. Because of the fan moves, there is a motor attached, the motor moves. I'm sorry, they call it generator. The generator moves. When the generator rotates, it produces electricity. That's the idea. So here this problem is related to a wind turbine. The blades of a wind turbine turn a large shaft at a relatively slow speed. What's a shaft?
Yeah, this one.
You studied mechanical subjects. If you don't know shaft, so
We don't know how to explain.
okay, explain in your own words.
It's like a car, like long pipe.
Long pipe. Anything round used for rotation. Anything round used for rotation, and even not necessarily round. Suppose this is not round, this is square shape rod, but if it is rotating like this, transferring energy by rotation. Okay, that's a shaft. Okay.
If you can make another word, when someone change place, take my place and will take it.
This is shift. This is shaft, S-H-A-F-T. It's, if you put I here, then it becomes shift. Okay, so okay. The blades of a wind turbine has a large shaft, turn a large shaft at a relatively slow speed. So wind energy turns means it rotates a very large shaft, big shaft. Okay, but the rotation speed is very slow. Okay, the rotational speed is increased by a gearbox that has an efficiency of 0.93. What's a gearbox?
Something that controls the shaft.
You remember by the car you have a gearbox, huh? What is a gear?
Something to change change the speed of something.
What is a gear?
You know the internal components of the.
I just want to know what is a gear. Any rotating wheel which has teeth. This wheel with teeth become gear. Get it? Any rotating. So if you know the clock, watch. If you remove the cover, you will see many gears in it. So gear is what? Any rotating wheel with teeth. So what you mesh, you mix different gears. So rotation of one is transferred from one to the other. But by changing the size of the gear, you can change the speed of rotation. And this thing you studied in dynamics. This thing you studied in dynamics, I think from chapter number 16. Exactly, from 16 onward. Okay, so the thing is that you have a very big shaft, but it is rotating slow. if it is connected directly to the generator, it will not produce much electricity. So what you do is that you connect it with a gearbox where a big gear is connected with a small gear, and when they are meshed together and when they rotate together, because the small gear has small size, so it will run fast. So you increase the speed. So once the speed is increased, now if you connect it with a generator, it will produce some sizable amount of electricity. Okay? So the rotational speed is increased by a gearbox that has an efficiency of 0.93. So obviously there will be some losses. So all the energy, all the wind energy which is coming to the wind turbine, which is rotating the main shaft of the wind turbine, will not be transferred to the smaller gear. There is some losses in between. Losses are because of what? Because you have mechanical components in contact with each other. There will be friction, there will be resistance, okay, and because of that some heat is generated. So where this heat is generated from? From the energy of the wind. So not all the energy is transferred. So there is an efficiency. Part of the energy is lost. Okay. So that's the wind turbine, and that's the gearbox. Within the gearbox, the energy of the wind, 93% is transferred to the low diameter shaft. Okay.
So what is the direction of movement that you see?
It's not mentioned here, the direction of motion. Okay. So obviously when the two gears are in mesh with each other, okay, again there are different gear arrangements. You can have a gear where one gear is meshed with another gear, or you can have a gear such that you have internal teeth and it is meshed with another gear which has external teeth. In that case the directions would be same, otherwise directions would be different. It's not a matter of concern here, what is the direction. Okay. In turn, the gearbox output shaft drives an electric generator with an efficiency of 0.95. So once the energy is transferred to the low or the high speed shaft, it is now connected with generator and it's generate electricity. But not all of the energy coming to it is converted into electricity. 95% of it is converted into electricity. So first there is a drop in energy, then further drop in energy. Okay. Where is this energy lost? All the energy is lost as heat. All the energy is lost as heat. So if you have a very high speed rotating pipe, after the rotation is done, if you just touch the pipe, it will be hot, because there is some loss of energy as heat. Okay. So the cylindrical nacelle, the definition is given. The cylindrical nacelle which houses the gearbox, generator and associated equipment is of length 6 meter and diameter 3 meter. This nacelle is basically a cylinder, a covering box, so that in this box you have the gearbox and the generator. Okay. So this covering box is a very large box, length 6 meter and diameter 3 meter. My height is how much? 1.8 meter or 1.7 meter. So it's the size of this room. That's why they put a man here, just to show that how big is this nacelle. Here they put a man. Okay. So the cylindrical nacelle which houses the gearbox, generator and associated equipment is of length 6 meter and diameter 3 meter. If the turbine produces 2.5 megawatt of electrical power and the air surroundings are 25 degrees centigrade and the surrounding is 20 degrees centigrade respectively, determine the minimum possible operating temperature inside the nacelle. So the thing is that wind energy is running the turbine. The turbine runs transfer energy to the gearbox. The gearbox runs the generator. Okay, but in between energy is lost. So all the wind energy is not converted into electrical energy. Part of it is lost. Where does the lost energy goes? It converts into heat. What will happen to the heat? Heat will raise the temperature inside. Okay. However, once the temperature of this nacelle, of this cylinder increase, what will happen? It will radiate energy and convect energy out. So heat will be transferred to the surrounding by radiation and convection. In the end, we need to find out that what will be the temperature of this nacelle under steady state conditions. Obviously, it will be high, but how much? What will be the temperature of this box?
The true temperature means inside the nacelle and the outside, 25 and 20.
T infinity is 25. T infinity is used for convection, right? So convection will be outside the box, right? So outside the box you have the air, and whatever the temperature of the air is T infinity. When we say surrounding, T surrounding is used in radiation formula, and that's the temperature of the sky you can consider, outside temperature. The air temperature would be slightly higher because the air is passing through this. Okay? So that's the mean temperature of the air, and that's the surrounding temperature of the sky, or you can say outside temperature. Okay. The emissivity of the nacelle is epsilon 0.83, and convective heat transfer coefficient. Convective heat transfer coefficient is H 35 watt per meter square Kelvin. Surface of the nacelle that is adjacent to the blade hub can be considered to be adiabatic. This statement is very important. What does this statement tell? Read it and let me know. The surface of the nacelle that is adjacent to the blade hub can be considered to be adiabatic. What does adiabatic means? No heat can be transferred. So that means there is no heat loss or gain. Okay? The whole body of the nacelle is rejecting heat, except the hub portion where the blade is attached. That portion is considered to be adiabatic. So that is not rejecting any heat. So if this is my nacelle, and here it is the blades with the hub attached, so only this portion can be considered adiabatic, but all other portion is rejecting heat. Okay? Yeah, yeah. And solar radiation may be neglected. Since this is a wind turbine and it will be outside, so might be some solar energy is also falling on it, but they said neglect the solar energy right now. Okay? Do you understand the problem statement? Okay. What we need to find out? We need to find out what will be the temperature of this hub, or what will be the temperature of this nacelle. Okay. And why its temperature is rise? Because the energy coming from the wind is not all converted into electrical energy. Part of it is converted into heat. The heat will raise the temperature of this nacelle. Now, what will be the temperature of this nacelle? That's what you need to find out. T surface. So we need to find Ts. Is it okay? Do you understand the problem statement here? Okay.
This is just for
Hmm?
this is just for
Yes. That's the thing. That's the thing. Surface temperature of the nacelle. That's the thing. As I said, it's not just how to apply these equations which is important here. In heat and mass transfer, the biggest problem is not this thing. The biggest problem is first understand where it has to be applied. Understand the scenario. Now you are working on a wind turbine. The next example is about a human body. Okay? So the thing is that first understanding the scenario and then applying. So there are two things in here. The first thing is more important and more difficult. Okay. Now, basically, first thing we will do is that we will apply the first law of thermodynamics. And first law of thermodynamics is very simple. Energy in, since there is no energy stored, so energy in is equals to energy out under steady state conditions. Okay. So what is the energy in here? Okay. So energy in is the wind energy, right? That's the wind energy. So if I call it that W dot is the wind energy, Okay. Now, once the wind energy come, where does it go? Inside.
No, not to pass.
What happened with the wind energy? Part of it is converted into electrical, another part is heat. So this wind energy is converted into electrical energy. Let's call this, or instead of E, we call it P, let's say, because they use it P, I think. Okay. So it converts into wind electrical energy, which is power, plus heat, Q, right? So this is the first law of thermodynamics. Energy in is equals to energy out, when there is no storage of energy under steady state operation. This is what? This is first law of thermodynamics. That's energy in, that's the energy out. Do you understand this or not? Okay, good. W is the wind energy input. This is then what happened to this wind energy? It converts into output plus heat. Okay. This is the thing we need, because this is the heat which will be then radiated by convection and radiation. So first we need to find this thing. If we find this thing, then we will move ahead. Okay. Now, wind energy and the output, they are related. And what's the relation? You have wind energy, I don't know how much, input is not given, but it is given that the turbine produces 2.5 megawatt, right? So you know what is P. It is 2.5 megawatt, right? But you know one thing, that whatever the input energy is there, when you multiply it with the efficiency of the gearbox and further multiply it with the efficiency of the generator, this will give you the output power, right? So as I said, that we need to find this Q to further solve the problem. Now we know this P, this output power is given, but we don't know how much is the input power. But since the efficiency of the gearbox is given and efficiency of the generator is given, we can find what is the input power. Because the input power multiplied by the efficiency of the gearbox, then whatever the answer multiplied by the efficiency of the generator will give you the output power, right? So this is known, this is also known, this is also known. So you can find what is W, input. Is it clear?
Yes.
So we have this efficiency of the gearbox, we have the efficiency of the generator here. Okay. So now you find the Q. So you know W dot, you know P, you can find what is Q.
I think we can know the Q from the convective, because give me the H and give me the T infinity and T so on. And the area.
You have T infinity, T surrounding. No, this is not T surrounding, this is T surface.
Yeah, yeah.
Surface you don't know. This is what we need to find, right? From the beginning. So we can find what is Q here. Is it clear till this step or not?
Again, this is how you find W.
How I found the W? Oh, look, this is the input power. Input energy multiplied by the efficiency of the gearbox will give the energy transferred to the generator. Multiply by the generator efficiency will give the output power. Okay, so whatever, let's say 100 was the energy incoming, so 100 multiplied by this, so 93 will be going to the generator. Then 95% of 93 will be converted into power, right?
So P we have.
But we have P, we don't have W dot. Okay, is it clear? So now we know Q. Now one thing is very clear, this Q is the heat generated within this nacelle, and it will be obviously radiated and convected out. Okay, so this Q is basically Q convected plus Q radiated. Is it clear?
Say neglect.
Hmm? That's a solar irradiation. Okay. Is it clear? Now you know this Q, right? So let's come over to Q convection. For Q convection, do we need this? Do we have this H? This H is given. Okay. Now let's talk about the area first. Let's first talk about the area. What will be the area of heat transfer? There's heat being transferred, right? Because of the radiation and convection. Heat is being lost, transferred outside. What will be the area? Yes, the surface and one side of the cylinder. Other side is the hub. Hub is adiabatic. Okay, what about the surface? What's the formula for the surface area of the nacelle? Pi dl, good. Pi dl, but that's not all, because you have the surface plus one side. So one side, what will be the this side area? Pi over 4 d square, good. So that will be the surface area, pi upon 4 cross-sectional area, d square, right? You know the diameter, you know the length. It's given, the length of the nacelle is this and diameter is this. Okay, so you know what is the area. Is clear? So
from where they bring the pi over 4 d square?
anybody can answer him?
Plus after the
Good? Thank you. Okay, so we know this area, right? Now, T surface is something we need to find. Question mark. T infinity is given 25 degrees centigrade. Don't mix here, okay? Many times T infinity and T surrounding are same, but if they are different, then it is provided. So here it is different. T infinity is the temperature of the air. T surrounding is the normal atmosphere temperature. Okay, the weather machine or the internet which tells you, okay, today is that much is the temperature. Okay, that's the T surrounding. That's the surrounding. Okay, so T infinity is known. So this thing, okay, only Ts is unknown. Plus Q radiation. A is known. Ts unknown. T surrounding known. For HR, do we know epsilon? Yes, this is known. Sigma is a constant. Ts is unknown. T surrounding known. Ts is unknown. T surrounding known. So what you get is that a very big equation, but only one unknown. Ts. It's a big equation now, but only one unknown. Ts. So you can find Ts. So finding it will be a bit difficult. Yeah, I'm sure about that. But the thing is that even they did it by trial and error method. They did it by trial and error method. Trial and error method is that you have the complete equation, then you just randomly put the values and see if the equation satisfies. In case if there is a problem, either I will provide you the values such that you do not need trial and error, either I will provide you in the exam values such that you don't need trial and error, or if you need trial and error method, then the answer would have no points. So the marks will be till the second last step. Okay.
For the Q, always the Q with convective plus the radiation Q.
Not necessary. You have to.
Didn't say how the question radiation or something for the heat radiation.
But you have to imagine, you have to understand that in this scenario only the possible ways of heat rejection is by convection and radiation. Okay.
So the shaft is not in the air.
It's in the air.
Yeah.
It's in the air. That's why radiation loss will be there as well. Air gives very little resistance to radiation. So radiation passes very easily from air. Yeah, water gives a huge resistance. So if there is water, then you can consider radiation neglected. Yeah, if it is solid wall around or something, then radiation is also neglected. Cannot pass through that. Okay. Okay. Is there anything that you do not understand in the solution? Okay. So problem solved, but if you see the problem, the biggest difficulty in the problem was understanding the problem itself. Okay. Applying it is something else.
Victor, with each problem, new strategy.
Almost. This is the problem with this course. I'm telling you again and again. This is the problem. You see the homework problems. Each homework problem, if you try to solve, if I have not provided you the solution manual, and if you try to solve it yourself, it will take one day for you to just solve one problem. You have to understand what is it in it, how to apply it.
So one was missing, Victor. The whole problem is missing.
Yeah.
So what can happen in the exam? You have to more in the quiz.
Normally, I give exams such that memorization will not help much. You can memorize if you want, but it will not help much.
That's the question, not the answer.
Okay. Okay, no problem, no problem.
Doctor, we'll talk with Dr. Ibrahim Jamal, so I don't need to talk with him.
Yeah, don't need to talk with him. I will talk with him.
I said, Doctor, he wants to change just the section. Because what section A is,
Whatever, I don't know, whatever, but just give me the timing.
okay.
Okay. Okay, so let's move forward. Now this is surface energy balance. Surface energy balance is a concept of basically first law of thermodynamics, and it says that suppose this is the body, this is the surface, okay, and you somehow you are getting it heated. It's getting heated somehow, okay. So what will happen to this heat? The heat will transfer from one end to the other end by which phenomena? Conduction. It will transfer from this end to this end by conduction, and then whatever the heat transferred from this end to this end will be transferred out by convection and radiation, right? That's the surface energy. So if you consider this surface, so total amount of heat which is conducted is equal to the amount of heat which is convected plus radiated. You get it?
Yeah, yeah.
There is the surface cannot store any energy. Okay, so whatever the heat comes as conduction will go out as convection and radiation. Okay, so Q conduction is equals to Q convection plus Q radiation. That's the surface energy balance. This is surface energy balance. So you have a surface, you have a body, here temperature is T1, here temperature is T2. T2 should be less than T1 so that the heat can flow. But once it flows through conduction. But once it reaches this surface, then all the amount of heat which came here will go out as radiation and convection. Okay. So this is basically also the first law of thermodynamics actually. First law of thermodynamics say E in minus E out is equals to 0 if there is nothing stored. So regarding this we have a numerical. Humans are able to control their heat production rate and heat loss rate to maintain a nearly constant core temperature of 37 degrees centigrade. All humans, our body core temperature is what? 37 degrees centigrade. That's the core temperature of our body. So whether I'm living in Saudi Arabia in summer where the outside temperature is 45 to 50 degrees centigrade, my core is maintained at 37. Whether I'm in Canada in winter where the temperature might go to negative 30 degrees centigrade, my core is still at 37 degrees centigrade. So the core maintains its temperature. You travel to Canada, then you travel to Finland, then you travel to some Asian country, then wherever. You travel the whole world. Your core temperature will not change. Outside temperature is changing. So how does this happen? This is a phenomena within the human body, and that phenomena is known as thermoregulation. Thermoregulation is because constantly heat is generated within the body, and the amount of heat generation is such that the core is maintained at a temperature required. Okay. The core temperature is very important. The whole human body phenomena is hugely affected by the temperature of the core that we have. When we have fever, our core temperature rises, and just a slight rise in the core temperature, you won't have digestion in food, you won't be able to do anything. You'll become weak and everything goes wrong. So core temperature is very important, and this is a phenomenon known as thermoregulation. It's inbuilt within ourselves by God, that it maintains, the core is maintained. And the idea is that how it is maintained, there is a continuous generation of energy inside. And since there is continuous generation of energy, it means there is a continuous loss of energy from our body as well. Because if there is no loss of energy, our core temperature will rise.
Yeah.
Right? So there is a continuous loss of energy at the same time. So so we have a constant core temperature of 37 degrees centigrade under a wide range of environmental conditions. This process is thermoregulation. From the perspective of calculating heat transfer between the human body and its surrounding, now we are interested in determining the heat transfer between the human body and its surrounding. Okay, we focus on the layer of skin and fat. So heat is generated inside, but when it has to go out of our body, first it will pass through the layer of fat. Now I have a big layer of fat, but previously I had a small layer of fat. So first it will pass through the layer of fat, then it passes through the skin and then goes out. Okay. With its outer surface exposed to the environment and its inner surface at a temperature of slightly less than the core temperature, approximately 35 degrees centigrade. So suppose this is my skin and the fat together. This is the layer of skin and fat. This is outside. This is my body, human body.
So the layer can be considered as one?
Yeah, consider fat and skin together as one. Okay, this is skin, fat layer. Okay. So a human body is maintained at 37 degrees centigrade, but let's say that this just below the skin fat layer, this surface is maintained at 35 degrees centigrade. Okay. Consider a person with a skin fat layer of thickness 3 millimeter. So suppose you have a person whose skin fat layer is only 3 millimeter. Maybe Ibrahim. Thin, he's a thin person. Okay. No fat at all. Okay. Maybe if it is in meters, then it's me. Okay. Okay. And effective thermal conductivity. So the thermal conductivity of this layer is approximately 0.3 watt per meter Kelvin. That's the thermal conductivity. Okay. The person has a surface area of 1.8 meters square. Then it might be served because 1.8 meters square means he's a tall guy. Okay. So the person has a surface area of 1.8 meters square. So the whole body surface area is approximately 1.8. So area is 1.8 meters square and is dressed in a bathing suit. Okay. So you have to dress in a bathing suit. The emissivity of the skin emissivity is, yeah, so epsilon is equals to 0.95, right? When the person is in still air, what is a still air? Like the air here. It is the air, no, still means it's not moving. So the air is here, but do I feel the wind? There is no wind. It's just regular air, still air. So when the person is in the still air at 297 Kelvin, so T infinity is 297 Kelvin. Okay. What is the skin temperature and rate of heat loss to the environment? We know the temperature just below the skin. We know that temperature, its inner temperature at the surface slightly less than the core temperature. So that's the inner temperature. Okay, so skin fat layer inside temperature is 35 degrees centigrade. We don't know what is the skin temperature. Okay, so this is what we need to find out. Determine the skin temperature and the rate of heat loss. Rate of heat loss means Q. So we need to find Q and we need to find Ts. Convection heat transfer to the air is characterized by a free convection coefficient of 2 watt per meter. H is given. Convection H is given. Is it clear? Now here it is given T infinity. T surrounding is given or not? It is not given. But it could be considered as same as T infinity because it is still air. Okay. Normally when the air is moving, then there is chance that the temperature of air is different from the outside. Okay. But when the air is still, though we can consider that the air temperature is the same as the surrounding temperature. Okay. So is the problem statement clear? So you have the human body temperature 37 degrees centigrade, but the core, just below the skin fat layer temperature is 35 degrees centigrade. Okay, and the skin has thermal conductivity 0.3, epsilon 0.95, area is 1.8 meters square, T infinity is 297 Kelvin. We need to find what is the surface temperature and what is the amount of heat loss. Okay, first of all, will there be a heat loss? 297 Kelvin means how many degrees centigrade? 273 is 0, and 283, 293, 24, right, 24. So that means 24 degrees centigrade. So obviously if the skin downside 35 degrees centigrade, outside temperature is 24 degrees centigrade, there is temperature difference, so there will be some heat loss. And it makes sense in any case. Wherever there is a crowded area, the temperature rises because everybody is everybody is losing heat. So all the heat goes into the environment. That's why in the Hajj you see too heated. So anyways, this is a problem. Now we have to apply the surface balance. Surface balance says that at the surface the amount of energy conducted is equals to the amount of energy convected plus radiated. Okay, so as for the surface energy balance, Q conducted is equals to Q convected plus Q radiated. Right? That's the thing. Let's talk about Q conduction. P by delta X. Right? Okay, so K, do we know K?
Yes.
K we know. Do we know area? Area is 1.8 meters square. Okay, do we know delta T? Tell me what will be delta T? Look, we have to apply the delta T in the area where the heat transfer we are considering. So we are considering heat transfer from the skin the inner side to the skin outer. Okay, so this we know 35, but this we don't know, Ts. Remember, delta T is always applied in the area where conduction is occurring. 37 was just given for your knowledge. Okay. So since we want to find where is the conduction occurring? Conduction occurring between the skin fat layer. So we need to consider the inner and outer surface of the skin fat layer. So the temperatures of the inner and outer surface of the skin fat layer is important. That is the region for which K is given. So you use this K for this region. So the temperature should be for the inner, between inner and outer. Inner temperature you know, 35. Outer do you know?
We can take from the still air.
It is TS surface.
It is Ts, surface of the unknown. This is we don't know. T infinity is the outside air temperature and they are not same. Very clear? So this thing delta T will be T inner. I can say T inner minus Ts. T inner is known but Ts is unknown. Okay? What about delta X? Huh? Known. This is known. This is the thickness, 3 millimeter. Remember, use in the only in the basic SI units. So 3 millimeter converted into meter. This was the same case in the last problem as well. I forgot to mention. You were given value in megawatt. So you convert it into watt. Okay. Anyways, so you get this Q conduction. Only Ts skin unknown. Okay. Now let's talk about Q convection. Q convection is H given, A given, Ts again unknown, T infinity given. So in Q convection again Ts is unknown. Let's talk about Q radiation. HR is epsilon given, this is known, Ts is unknown, T surrounding as I said that consider it same as T infinity, Ts unknown, T surrounding same as T infinity. Area given, Ts unknown, T surrounding given. So one unknown. So you get one equation, very big equation when you substitute everything, but only one unknown. So they also used again here trial and error method.
We don't see the trial. Just we see the name.
See the answer above.
So you see the
See the answer above.
see you got this big equation, and in the end they somehow they use trial and error. Okay. Anyways, in this problem,
I have to a second.
yeah, this was the first part.
Yeah.
So you solved the first part. Is the first part solution clear or not?
Yeah.
Okay. Once again I'm telling you, if there is a problem where in the end you need trial and error, then I will not put any mark for the final answer. I will just put mark for the second last step, till the second last step. I'm not testing your mathematics skills here. Yeah, if it was a class of mathematics, then I would definitely test that. Okay, so part 1 is done. Let's talk about part 2. If the person is in water, previously the person was in the still air, now the person is in water. No radiation, exactly. So if the person is in water, T infinity is 297 Kelvin. Okay. What is the skin surface temperature and heat loss rate? Again, the same two things we need to find. Okay. Heat transfer to the water is characterized by convection coefficient. Now H is different. So it's the same problem, only the thing is that this time radiation is not there. Okay, radiation is not there. So this term is not there. H is now different.
The temperature of the surrounding would be the same as it's given as the T infinity.
Do you need temperature of the surrounding?
I don't
Radiation is not
know, radiation is not.
radiation is not there because you are in water. Okay. So
Just water, there is no radiation.
any fluid normally. I mean any liquid. Any liquid.
Specific materials.
No, any liquid. Yeah. So if it is solid, no radiation can pass at all. if it is water or any other liquid, radiation pass is negligible almost. You can neglect it. In air or any other gas, radiation will be there. Is it clear? So it's like resolving the problem again, but this time just make these changes. So that's the solution. This is a part 2 of the solution. Once you have found out Ts, then finding Q is very easy. Okay, Q is either Q conduction or addition of these two. This is Q loss. Okay.
No need to do the equation.
Yeah, just use Q conduction is good enough. Okay, so that topic is over. Now we move towards the last topic of the most easiest chapter that you are going through. Okay.
How many questions, homework?
Hmm?
Is there any homework in this chapter?
Every chapter has homework.
Okay. How many questions in this chapter? In this chapter? Every month. Okay, good. Okay, this is.
Like need more.
No, Doctor.
These.
We'll talk about it.
No, we don't.
Okay, relationship to the second law of thermodynamics and the efficiency of heat engines. This is the last topic for this chapter as an introductory chapter. You studied heat engines in thermodynamics and you become experts in that. Okay, so so let's apply this concept of heat engines. You know that the efficiency of heat engine is work output over Q in. You remember that? So efficiency of heat engine is work output over Q in, or we can write it as Q in minus Q out over Q in, or we can write it as 1 minus Q out over Q in. Or if we talk about the Carnot efficiency, so Q's can be replaced with temperatures. Okay, so for Carnot efficiency, it will be 1 minus Tc over Th. Okay, cold sink temperature over the hot source temperature. Okay. So this is what we studied before, and that's not wrong. But we have to understand one thing. Look, you have a heat engine. A heat engine could be Rankine cycle, could be any other cycle, okay? And you use energy, heat energy, and produce work. And in the meantime, you reject some heat. The heat rejection is normally done by which component? Condenser. Condenser reject heat, right? Heat is supplied to the boiler, right? Now, heat rejection is done at the condenser. Now suppose condenser is rejecting heat to the air outside, say air in this room. Air in this room would be at what temperature? 21, 22, maybe let's say 24 degrees centigrade. That's the comfortable range. So that would be the temperature of the room, okay? So if I have a condenser and it has to reject heat to the air in this room, the temperature of my condenser should be slightly higher than the air temperature inside. Because if there is no temperature difference, heat will not be rejected. So if the room temperature is 24, the temperature of condenser should be greater than 24, so that the heat rejection is possible. Otherwise, you cannot reject heat. Got it? So normally heat rejection is done to the sink, and in this case this room becomes our sink, right? But here the temperature that we consider is for the sink. However, this is wrong. If we consider that the condenser is also operating at 24 degrees centigrade and the temperature of the air is also 24, it cannot reject heat. That's not possible. You need a temperature difference. So probably the temperature of the condenser would be slightly higher than the room temperature, right? So the TC is not correct. It's not correct to use TC, because here it is the heat engine we are talking about. Okay, this is our heat engine. We have the source, we have the sink. Energy goes in, energy goes out, right? And this is the heat engine. This is the heat engine. This is the work output. Okay, we are using the temperature of the source and the sink. In this case, our sink is this room. Let's say 24 degrees centigrade, and here we have the condenser, which is rejecting heat to the sink. So TC, if we consider this as TC, this is wrong. Our TC should be here, right? Should be the condenser temperature. And it should be slightly higher than the room temperature, right? So instead of using TC, let's call it TCI, because TC is the sink, but our temperature would be slightly higher than TC. So let's say this is TCI. Let's call this TCI. Now it's realistic. Get it? Similar case is here. You have the source supply heat to the heat engine, right? If the source is supplying heat at 200 degrees centigrade, within our Rankine cycle or whatever cycle we are using, within our cycle, the temperature of the boiler should be slightly less than the temperature of the source. We want the energy from source to go into the boiler. Energy will transfer from source to the boiler if the boiler temperature is slightly less than the source. If they both are at the same temperature, energy will not transfer. You get it? You want the energy to flow from source to here is our boiler. You want the energy to flow from the source to the boiler. But for that to happen, for this flow to occur, the temperature of boiler should be slightly less than the temperature of the source. You get it?
Yeah.
So that means if this temperature is TH, then using TH would be wrong. So let's call this here THI. So if we use THI here, now this is correct. Is it clear? Do you understand this concept or not?
Yeah.
So, so this same diagram is drawn here, but drawn in a different way. We put it like this, but this is the source, this is the sink, this is our system. Okay, sorry, this is our system. Okay, now remember, whenever the heat is transferred from one temperature to other temperature, for example from TH to THI, it will be transferred by a medium. There is going to be some medium in between, and that medium will offer some resistance. So you will have a resistance on the hot side, and then similarly from TCI to TC, when it will be transferred, so there will be a resistance in between, and that would be the cold side resistance. You have the hot side resistance, you have the cold side resistance, right? So now we know that 1 minus TC upon TH is wrong. We know that this is right, but it has one problem. The problem with this equation is that although this equation is correct, the problem with this equation is that we need to find TCI and we need to find THI. That means we need to go into the cycle to find these temperatures. which is quite a hectic thing. It's easy to find the source and the sink temperature. The sink here, for example, is this room. It's easy to find the room temperature than to go into the cycle and find out what would be the temperature of TCI. Similarly, it's easy to find the source temperature than to go into the cycle and find what is THI. If you know TCI and THI, then this equation will give you the correct value of efficiency. But for this, you need to know the TCI and THI, which is hectic, which is troublesome. You need to go into the system. Okay, so what we need to do is we need to find an equation which, instead of using TCI and THI, which still uses TC and TH. But we can find a more easier thing is that we can find out these resistances, resistance on the hot side and cold side. They are comparatively easily available. Okay, so use those values and the value of TC and TH. So now there is a mathematical manipulation, and that mathematical manipulation is there in your book. I have not put there in the slides, but you have a homework problem related to that. So you might need to go through that mathematical manipulation. And they come up after going through that mathematical manipulation. This is the answer. So it is 1 minus Tc upon Th minus Q in R total. R total means resistance of hot plus resistance of cold side. Both side resistance in totality. So how do we get from here to here? This thing is equal to this thing. This thing is equal to this thing. Okay. But how do we get from here to here? This is, I think, one-page mathematical derivation, manipulation. Just put. You need to go through it because you have a problem in the homework as well. And so if this kind of problem comes in the exam, first I will ask you to drive this, then use this. So first you will have to drive this, that what is the formula, and then after the derivation is done, then you will use this formula. You need, because the formula is not given to you. You'll have to first drive it. Okay, so now let's have a problem related to that.
This needs manipulation.
Huh?
This exam needs manipulation.
Yes. In a large steam power plant, the combustion of coal provides a heat of Q in 2500 megawatt. So Qn is given. This is Qn. Okay. At a flame temperature of TH 1000 Kelvin, so TH is given. Heat is rejected from the plant to a river flowing at TC 300 Kelvin. TC is given. Q in TH, Q in TH, TC given. Heat is transferred to the exterior of large tubes in the boiler by the way of radiation and convection through the boiler tubes by conduction, and then from the interior tube surface to the working fluid by convection. On the cold side, heat is extracted from the power plant by condensation of steam on the exterior condenser tube surfaces through the condenser tube walls by conduction, and from the interior of the condenser tubes to the river water by convection. Hot and cold side thermal resistances account for the combined effects of conduction, convection, and radiation, and under design conditions they are. So hot side resistance is given and cold side resistance is given, but here you have to use the total. It means hot side and cold side together. Although it's a very big question written, but in reality all the values are directly given. TC given, TH given, Qin given, R total given. No, I mean here in this question, question looks long, but everything is directly given. So now once you know all these parameters, just substitute the values, find out the efficiency. Determine the efficiency and power output. Power output would be what? If you know the efficiency, multiply by the Q in will be power output. Okay? If you know the efficiency, multiply by the power in is equals to output. Okay? And power output accounting for heat. Okay. Over time, coal slag will accumulate on the combustion side of the boiler tubes. This fouling process increases the hot side resistance. So now in the second part, your R value changes. Hot side resistance is this. Now cold side resistance is this. Again, find out the efficiency and the power output. So in reality, it's not a complicated problem. The complication is here, converting from this to this. Because this formula is not given. This formula is not given. So you have to find out this formula by this mathematical manipulation and things like that. And you have one problem. This problem is about heat engine. In the homework problem, you have the problem about refrigerator. You remember what was the difference? Okay. Yes. Heat pump. The process here is known as fouling process. This process is the one which increases the resistance here. Now, you go on the internet and search about it. What is fouling process? This is something I can ask you in the exam. Write 2-3 sentences about the fouling process. Why does it increase the resistance? It says that the fouling process increases the resistance. Previously resistance was this and this. Now because of the fouling process, resistance is this and this. Why? What is this fouling process? This is something, go and search on the internet. Okay. So anyways, this problem is solved here. The solution is, as I told you, is just once you have the formula, just directly put in the values. Mathematical manipulation is not present here and in the slide, but it is there in your textbook. Go through it. Okay. And with this, complete your first and the most easiest chapter of the heat and mass transfer. This is basically the introduction, there was nothing new in it. I tell you right now, you are still looking at very easy things. Chapter 3 will be the most difficult chapter there. Okay? So, because in chapter 3, there is a lot of differential derivations, differential equation derivations. Okay? So, like 2 to 3 page. The whole numerical itself is a derivation and differential equation derivation. Okay. Okay. That's good. So chapter number 1 is done. We for the last 2 days we have been a bit slow. From tomorrow, inshallah, we will start gaining a little more pace. Okay. So tomorrow we will finish, inshallah, chapter number 2.